Way back at the very beginning of artificial intelligence, there was this simple, elegant algorithm that made a huge promise. It could learn to tell the difference between just about any two things. And it did it by just drawing a line. This is the story of the perceptron and how its biggest weakness actually became its most important legacy.
It really all boils down to this one simple question. But it's a question that's at the heart of so much of AI. I mean, think about it. You've got two groups of things, say apples and oranges, or even spam emails and important ones. How do you actually teach a machine to see the difference, to draw that line in the sand and make a decision? That's the fundamental problem we call pattern classification. So to really get a handle on the perceptron, we need to rewind the clock a little bit, back to the early days of neural networks, when the very idea that a machine could learn from a teacher was, totally revolutionary. Yeah, the idea of a thinking machine didn't just pop up out of nowhere. Back in 1943, McCulloch and Pitts laid the conceptual groundwork. Then, in 49, a guy named Hebb theorized how this learning could actually happen. But the real game changer came in 1958, when Frank Rosenblatt introduced the perceptron. This was the first algorithm really built for what we call supervised learning, basically learning from examples given by a teacher. So what exactly is it? Well, at its heart, the perceptron is the simplest neural network you can possibly imagine. Think of it like a single artificial brain cell. Its entire job is to look at some data, some pattern, and put it into one of two boxes. That's it. Sounds simple, right? But it was incredibly powerful. So how does it actually work? How does a bunch of simple math learn to draw this all-important dividing line between two different things? Okay, so the mechanics are actually beautifully straightforward. First, you give it some inputs. That's just the data you want to classify. Each of those inputs gets multiplied by a weight. Now, the weights are key. Think of them as little knobs that the machine can turn up or down to decide how important each input is. Then, it adds in a little something called a bias, which just helps nudge the final line around. And after all that, it spits out an output, a simple +1 for class 1 or a -1 for class 2. And this brings us to what is probably the single most important concept for understanding the perceptron, linear separability. This is both the source of its power and, as we'll see, its Achilles heel. All it means is that for the perceptron to do its job, the two groups of data have to be separable by a single straight line. And that is the perceptron's entire mission in life. To find that one perfect line, or to use the fancy term, a hyperplane if you're working in more than 2 dimensions, that cleanly slices the two classes of data points apart. This visual just lays it out perfectly. On the left, you can see that a single straight line can easily cut between the two groups. That's a problem the perceptron can totally solve. But on the right, well, the groups are all mixed up and intertwined. There's no single straight line that can separate them without messing up. That is a non-linearly separable problem. This whole idea of linear separability led to something really cool, the most famous part of the perceptron story, a powerful mathematical promise that had researchers incredibly excited. This is the core of what's called the perceptron convergence theorem, and it's a huge deal. It's basically a guarantee. It says that if your data can be separated by a line, the perceptron's learning algorithm is guaranteed to eventually find a solution. Not maybe, not sometimes, always. Just think about that for a second. It wasn't a question of if it would work. As long as the problem was solvable with a single line, the perceptron would find that line. This mathematical certainty was what made it seem so revolutionary at the time. But hey, enough with the theory. Let's put this promise to the test. We're going to run a little computer experiment that's going to show us both the power of this guarantee and what happens when it hits its breaking point. To do this, we're going to use something called the double moon problem. It's a classic test designed to see how well a classifier can handle different kinds of data. The goal is super simple. Draw a line that separates the blue moon from the red moon. So, in our first scenario, the two moons are clearly separated. See that nice, clean gap between them? This is a textbook, perfect example of a linearly separable problem. The perceptron should have no trouble with this at all. And boom, just as promised, the convergence theorem holds up. The perceptron finds that perfect dividing line without breaking a sweat. And it gets 100% accuracy on the test data. A flawless victory. Okay, but this is where the story takes a turn. What happens when the world isn't so neat and tidy? What happens when the data isn't perfectly separable?
Let's take those two moons and just smush them together and see what happens. So now, we've pushed the moons so close together that they actually overlap and intertwine. There is now no way that a single straight line can perfectly separate the red points from the blue points. Our problem is now officially non-linearly separable. And here's what happens. The algorithm completely breaks. Instead of finding a clean solution, the line it draws just kind of thrashes around, cutting right through both clusters of data. It can't settle on a correct answer because, well, a correct answer in the form of a single straight line just doesn't exist anymore. And this isn't just a visual failure. You can measure it. The perceptron now has an error rate of 9.3%. That means it's getting it wrong almost 1 out of every 10 times. The magic is definitely gone. But here's the crazy thing. This failure wasn't the end of the road. In fact, you could argue that the perceptron's failure was its greatest and most important contribution to the entire field of AI. See, in 1969, these two absolute pioneers of AI, Marvin Minsky and Seymour Papert, published a famous book called Perceptrons. And in it, they didn't just point out these limitations. They proved them with cold, hard math, showing exactly what this simple model could do, and more importantly, what it could never do. And this quote from their book just sums it all up perfectly. The perceptron became so important because of its limitations. By showing the world the exact point where a single neuron fails, it forced all the researchers to ask a really, really important question. And that question was, if one line isn't enough to solve complex, messy, intertwined problems, what's next? What if we used more than one line? What if we started stacking these simple perceptrons into layers to create complex, squiggly decision boundaries? And that very question is what paved the way for the deep neural networks that power our entire world today.